it like that. It's 1 o'clock, so I guess we can get started. Hello. Welcome to Math 322, Section 5. This is our Canvas page. I'm sure you've seen it by now. Yeah. So this is matrix algebra. I guess we'll just quickly go over this, what's on the Canvas page. The syllabus is on here. That's probably the most important thing. This schedule I've taken from one of the professors that's teaching this class this semester as well. He's taught it many times before, and so I'm just sort of following the same schedule that he has. It's possible that it could change slightly. If we get through material a little faster, we might cover more things. If we get through material a little more slowly, we might cover less things. But we'll stick pretty closely to it. I'll let you know as soon as I can if there are any changes to it, and I'll put them on the Canvas page. Let's look at the syllabus. Okay. Oh yeah, I should tell you my name. This is my name, Drew Duncan. Oh, oops. That's a little small. Let's zoom in. Okay, so I'm Drew Duncan. You can call me Drew if you want, or if it makes you feel more comfortable, you can call me Mr. Duncan. But not Dr. Duncan, because I don't have a PhD yet. Okay, let's see. Where's my packet? This is the textbook. This is the 5th edition. It doesn't really matter if you have the 5th edition or the 4th edition. Probably older editions work as well. I don't think there are huge changes. Mostly probably to the exercises at the end of chapters. Everything else is probably pretty close to the same. So if you want to save some money, you don't have to buy the book. You can just get an electronic copy somewhere of an old version. Let's see, technology requirements, none. This is an in-person class. We'll get to what that means in just a minute. But you don't need to use Zoom unless you want to come to my office hours, which will be on Zoom, or you can actually just come to my office. So my office is in the math house. Does everybody know where that is? Does anyone know where that is? No one knows where that is. Okay. So let's see, math house, UKY. So this is it's actually a house. It is, here's a picture of it. It's on Maxwellton. Everybody knows where Maxwellton is, right? Right across the street from the College of Law, I think, something. So this is a picture of it. It's over there. It's, they don't tell where the address is. Here we go, 654 Maxwellton Court. So if you want to come to office hours, you can just follow me over there after class, or I will also have a Zoom meeting open at the same time for people who want to talk on Zoom. Okay, classroom safety. I'm going to get this out of the way. I'm taking this pandemic stuff very seriously. If you feel at all even slightly ill, don't come to class. If you are not willing to wear a mask, covering your nose, completely covering your nose at all times, 6 feet apart at all times, don't come to class. If any of these things are a problem for you, I strongly suggest you transfer to an entirely online section. And there are some sections like that this semester. Yeah, I came in like a week ago and moved all the desks so that they're at least 6 feet apart. I came in with a tape measure and it took me like an hour and a half, so should be safe. Safe-ish. Okay. Any questions about that, by the way? Maybe I should stop at some point. Yeah?
If you're sick and we shouldn't come.
Keep your nose covered, please.
Yeah, if we're sick and we shouldn't come to class, is there going to be a recording that we can watch?
Yeah, okay. Let me come to that. Yes. Good question. I should probably talk about that right now. So All of these lectures are going to be recorded by something up there in the ceiling, and they're going to go onto the Canvas page. Hopefully everything is set up so that it works properly. So this is being recorded right now, and at the end of class it will be put onto Canvas. It might actually even be like live streaming right now on the Canvas page. I don't know if anybody wants to look at that and tell me in a minute. But yeah, lectures will always be recorded. Okay, yeah, and let me just jump down here to attendance. I put attendance policy to be discussed so everybody would come in today and hear me say all these things. I'm not going to take attendance. So attendance will not be part of the grade at all. These lectures are for us to have discussions. And I am much better at having these kind of discussions about mathematical topics in person where I can see your face and I can interact with you, right? And it's much more, I'm able to provide much more value to you, which is why I made the choice to have this class in person despite all of the problems that it was going to cause. So that's the idea. Now, if you would like to, if that isn't beneficial for you, if coming in here and talking to me in person isn't especially beneficial to you, you don't have to come in. If you have something better to do, you don't have to come in. If you're sick, you don't have to come in. You shouldn't come in. It's something that I've tried to set up entirely for your benefit. And so I'm not requiring anyone to attend lecture. I'm just trying to convince you that it'll be helpful for you. And you can ask me questions directly. It's a lot easier to do that than it will be if you're talking to me on Zoom or something like that. Exams will be held in person. They'll be in here. So there's no online exam part of this class, unlike the other sections. And, well, I'll come to, exams will be most of the grade. So the in-person exams that we have here will be a majority of the grade in this class. Homework. So there's homework on the web work. I've copied the homework from the other sections. I think pretty much everybody in here has probably used web work before. You know how to do it. You know how to get to it through Canvas and all of that stuff, right? Yeah, okay. Also, let me know if you can't hear me through this thing. It's like a sauna inside here right now. Yeah, we'll have web work. Worksheets are not going to be as big a part of this class as they are the other sections. My hope is that before you come into class, so you have the calendar on the Canvas page, my hope is that, my demand, is that you will read the section in the book before you come to class so that you will know what things you're having trouble understanding. And that's what we'll spend the time in here talking about, right? We won't waste time on things that are easy for you. We'll only talk about things that you're having trouble with. So that's the hope. The way we're going to structure the lectures is around what you want to know, okay? So make sure you know what you want to know before you come in here. The worksheets will just be sort of like another source of practice problems if you want to do them, but they're not going to be mandatory. There will be quizzes. The quizzes will be according to the schedule. 2 lowest quiz grades will be dropped, blah, blah, blah. It will be all online, and I'm not going to sort of do a thing where if you have trouble submitting something online, there's like going to be an extra extension and all this stuff. We're not messing around with that. The deadline is the deadline, so make sure you get stuff in when it's due on the Canvas quizzes. Okay, we'll come back to the exams so that I can talk about the grading. Why am I so sort of not really that concerned about the way we set up the homework and the quizzes? Because together they will only be 10% of the grade. The quizzes and homework, in my mind, are there just for you to understand, for you to get a sense of do you understand this? Do I really understand the concepts, the techniques that we're talking about in class? Am I able to apply this stuff? If you can't do it on the homework and you can't do it on the quizzes, you'll know immediately. And then you'll come in and you'll say, there's such and such that I don't understand. Right? And then I'll talk about that. I'll spend the class talking about that thing. They are not there to evaluate you. The only thing in here to evaluate your performance and for me to say to someone else if they ask, how good is this person at linear algebra or matrix algebra, is the exams. That's 90% of the grade. Okay? Okay. I'll pause again for questions. Any questions? Yes?
I might be giving away that I haven't read the entire syllabus yet here, but these quizzes, will they be, are we going to have a big window for them, or is it going to be like 10 minutes at the end of class time or something?
They won't be in here. They'll be online.
Okay.
They'll just be on campus.
I don't need to bring my computer.
No.
Okay.
Yeah.
That's good, because it's heavy.
Yeah.
Sweet.
Good question. Anybody else have any questions? I'm going through all of sort of like the rules and stuff at the beginning. It kind of makes me sound like I'm really kind of a hard instructor, but trust me, this class will be fun. It's a really interesting subject, and this is going to be a lot of fun. Okay. Any more questions? Any other questions? There'll be plenty of time for more questions later. Okay. Exams. 3, they're closed book, closed note. I don't know about calculators yet. I might just make the math, like the arithmetic, multiplying and adding numbers, easy enough that you don't need a calculator. But definitely closed book and closed note. As we get closer to the exam time, I'll decide whether it's closed calculator. They will all be cumulative, but they will be weighted towards the more recent stuff. So, just so you know. If you're wondering when it's okay to forget the stuff that we learn in this class, the answer is never. Okay, that's a little bit of a joke. Did I skip anything up here? Oh, course topics, we'll come back to that. Grading, academic integrity, don't cheat. Disabilities, DRC, it's a great place. If you have any kind of problems whatsoever, go and talk to them and they'll fix everything. They're fantastic. I'm not even kidding. They're really, really good. If you have any kind of problems whatsoever, go talk to them. Non-discrimination, don't discriminate. Class recording policy. I don't know, this is sort of copied from another professor's syllabus. These classes, as I've mentioned, they will be recorded and they'll be put on Canvas for the convenience of people who can't be with us. The instructor reserves the right to modify the syllabus at any time with proper notice, and proper is up to me. I'll try my best, I promise. And then here is, I think these are links to the web work. Maybe not. I don't know what this is. I don't know what this section is. I copied it from someone else. So I'll go really quickly to modules, web work for UK math, and this should go to, yeah, here we go, linear algebra. And this should be for us. And my understanding is that whenever you go into this, it automatically sets everything up you need to do the homework besides learning the material. Only you can do that. And so, yeah, it should work. Give it a shot as soon as at your earliest convenience, and let me know if there are any problems. And I'll try to fix them. Click below to what's going to happen if I click on this? I should mute it. I don't want feedback in case it goes crazy. Here we go. We'll see what happens. Oh God, there I am. Okay. Yep, it works. Anything else? Anything else? There's an announcement. Did everyone get this? Did you get an email saying this? Okay, perfect. People. Oh, yeah. So you all. Let's turn this off. So that I don't think it shows anything private, but just in case. I'm going to go through the names, not for the purposes of taking attendance, but to try to figure out if there's anyone here who's in the wrong classroom, or maybe somebody who didn't show up, which is fine. Trey Asensio. Hello. Tanner Banta. Okay. Connor Bergeron. Thank you. Daniel Blake. Morgan Demps. Oh, Richard Duncan, that's me. Oh, yeah. It says in here Richard Duncan. That's my actual first name, but I go by Drew. Matthew Eichelberger. Hello. Jonathan Irwin. Hello. Jordan Gatewood. Hello. Laura Rose Giltner. Hello. James Gosser. Hello. James Griggs. You've been in my class before. Yes. Good to see you again. Michael Haley. Tristan Harbold. Hello. Austin Herod. Hello. William Hodge. Hello. Matthew Jones. Okay. Mason Joseph. Hello. Amy Cobra. Okay. Thank you. And hello. Sam Kress. Okay. Will Lombardi. Jake Netherton. Hello. Anthony Nemo. Okay. Carson Palmer. Hello. Emily Powell. Morgan Rabe. Hello. Joshua Ray. Graham Smith. Hello. Anna Soriano. Okay. Juan Soto. All right. Clayton Wagner. Hello. David Webster. Oh. And Drew Willis. Hello. Okay. So if you didn't hear your name called, you are not on my roster, and so you should probably go check something out, like if you're in the right place or you're signed up for the class. Okay. Did I say, is there anybody? Does that apply to anybody? Okay, so we're not worried about it. Okay. The syllabus also has a section on course topics. Let's just jump right into it. Let's just start talking about what linear algebra is. Or maybe I'll kind of, I've got some notes, let me bring them up. And then I'll try to kind of put the subject into context. So, has everyone in here taken Calc 3? Is there anyone who has not taken Calc 3? Is it a prerequisite for this course? Are you required? Somebody know? I don't know. Oh God, I hope I remember my password. Oh, yes. Okay. All right. Yeah, so how about Calc 4? Has anybody not taken Calc 4? Yeah, I don't think it's a prerequisite for this class, right? I think maybe Calc 3 is. So let me start with a kind of, let's start in the center of the board. A kind of map of the math that you've probably seen so far. So you start off in elementary school or kindergarten, and you deal with counting numbers. Right? 1, 2, 3, 4, and so on. And then afterwards you progress to addition, and multiplication, and maybe after that, fractions or negative numbers, right? We're kind of working our way along. We're making things a little more complicated at each step. The sort of things, the ideas that we're dealing with are gradually getting more complicated. Algebra. So this is in equations. So, you introduce the idea of a variable, trying to figure out what the value of a variable is that satisfies an equation. You go here, and then functions. Functions are really the raw material for calculus. What else? Am I forgetting something here? Am I leaving something important out? Trig. Trig can go in here too. Trigonometry. So a lot of what we deal with in trigonometry are functions, sine and cosine, tangent, things like this. And they come up again a lot in calculus, right? This is one of the places where they get used a lot. You remember this from Calc 2, maybe. Okay, and then finally you reach the college summit of math, the peak, which is calculus. And then you look back and you sort of see that everything, all these concepts, we're building towards calculus, right? The classes, we were trying to go through as quickly as possible, get as many of these concepts as quickly as we could, going through this mathematical education until we got to calculus. And then calculus is the thing that we can apply in science and other areas of math and statistics and economics and all these other, amazing fields. It's very useful. But you see that we went sort of in a straight line getting there. We've only learned things in mathematics that would get us to calculus and nothing else, right? Everything else was sort of set to the side. One of the things that, for example, complex numbers were very common to be taught maybe around this piece right here. But since you don't need them for Calc 1 or Calc 2 or Calc 3, we've sort of pushed them aside from mathematical education. So it's not as common anymore to talk about complex numbers.
You say that unless you're an electrical engineer.
And then it's very important. Yeah. There's further ways you can go from calculus here, and in electrical engineering, they're very important for analyzing circuits and things like that. But most people's mathematical education looks basically like this, or they get to right here and then stop, right? Or some people get to right here and stop. Not us, right? Okay, so all of this stuff that we left out of math were other directions that we could have taken. And when we look at this equations and algebra right here, instead of going to more complicated things like functions, polynomials, right? These are also very important building blocks in calculus. Instead of going in that direction, we could go in a different direction, right here. And this direction is, instead of just having one equation that we're trying to solve, have systems of equations. So simultaneous systems of equations that we're trying to get solutions that satisfy all the equations at the same time. We see a little bit of this. In Calc 3, there's a little bit of this. Probably when you took pre-calc, you saw just a tiny bit of this. In Calc 4, you see a bit of this as well. But just a little bit. In Calc 3, it's usually systems of 2 or 3 equations, right? Because we're thinking about 2-dimensional or 3-dimensional objects in Calc 3. Okay, so this right here is the other direction that doesn't go directly to calculus. It kind of shoots off in its own direction and becomes something else. And this leads to the topic that we're going to talk about in here. These things are really hard to breathe in. Which is linear algebra, or as we call it in this class, matrix algebra. Okay. Now, what did I want to say? Okay. Does anybody have any feelings about this? We're taking a different direction. I remember when I was an undergraduate and I first took this course, math here at UK, Math 322, a long time ago. It was sort of the first time in my mathematical education where I just felt completely lost. It was like I didn't understand what I was trying to do at the time. It was really a shocking experience. So hopefully I can sort of not make it a shocking experience for you by putting it into context.
I can say I'm pretty excited about it because in electrical engineering we do big old circuits with tons of nodes and tons of loops, and I'm taking this class because I learned that matrices make that a lot easier to solve instead of a big stack of equations.
Yeah,
Systems,
exactly. Yeah, it's an interesting area. It's sort of well, it's kind of, I mean, what we think about this, they're linear equations. They're, if you remember polynomials, your linear polynomials were mx plus b, right? When you have one variable, everything falls into this form, and it's called linear. Or degree 1, because the highest exponent you see, I'm circling it, I'm not drawing, so let's try an arrow instead. The highest exponent you see on any of the variables, there's only one variable, is 1, right? So that's the degree 1 part. And the linear part, this comes from the idea that this is the equation for a line, a straight line, as long as the line is not vertical, and this covers all of them. Right? So this is sort of like the easy case, and it's kind of it's a humble beginning for a subject, talking just about straight lines and, well, higher dimensional analogs of straight lines. I'll come back to this in just a second. But it's a humble beginning for a subject that turns out to be foundational to pretty much everything in mathematics and of tremendous importance to every field of science, at least as important as calculus. Calculus is very important. You can't state the laws of physics without differential equations, right? Linear algebra, it turns out to be just fundamentally important to so many things. I'm going to try to skip the application, the idea of talking about applications of this, and just go straight to the thing itself, which is linear algebra. Okay, so we start off with the equation of a line, and there's a way that we can change this up a little bit. We can rearrange the way that we write things, and instead of saying something like y equals mx plus b, we can say ax plus by equals c, not the same b, a different b. Just some variable, or some constant a, some constant b, and some constant c. And these specify every single line, right? Every line in the 2D plane, right? So what we have here are two variables. I'll just write the whole word, why not? And the way that we typically represent two variables existing simultaneously, two variables that are connected to each other, is in the coordinate plane, where this is the first variable. We give some kind of arbitrary ordering to the variables. We say one of them is first, that's horizontal, the other one is the second one, that's the vertical one. And then all of these things give every single possible line that we can put. Every every line in a 2D plane. These thick masks, it really is hard to breathe. It really is. Once you get started moving, okay, it's like being at a high altitude. I'm just going to get stronger because of this. Okay, so every line, and what is a line? A line is fundamentally a one-dimensional object, right? It's a 1D thing in a 2D space. This is the whole space. This is the thing that we're talking about. And there's some equation that specifies it. We can figure out what A and B and C are based on finding a point and another point on the line. Or, going back to this form, finding a point in the slope, et cetera, et cetera. So this is going way back in time. This is going all the way back to pre-calculus stuff, right? Or Algebra 2 or whatever it's called. Okay. Why is it that when I write out an equation like this, it's got two variables, it says something times the first variable plus something times the second variable equals something. Why does this give me a one-dimensional object? There's a good reason for that. If I take this equation, ax plus by equals c, and I say x is arbitrary. Okay? I'm going to just make the declaration that x can be any number. We should be a little careful about what kind of numbers we're talking about. Oh, right, because we started off with counting numbers, and then we moved on to fractions, and at a certain point we moved on to real numbers. Right? Numbers that can't be represented as fractions, numbers that don't have a repeating or terminating decimal expansion, irrational numbers. We decided that we wanted to include those in our number system. So we just made that declaration. We declared our number system is now real numbers. And for whatever reason, we chose not to say our number system is complex numbers. Okay, so let's say is an arbitrary real number. And now what can we do? Through the magic of what we call algebra, we found that once we know what x is, we can figure out what y is. We subtract ax over the other side and we get by equals c minus ax. And then we divide by b and we get y is equal to c minus ax over b. And we see that y is completely determined. If we know what x is, we can determine completely what y is, and vice versa, with one exception. Can anybody tell where the exception comes in? What step might something break down here in this whole process of reasoning? So now you're thinking like a mathematician. B could be 0, that's right, yeah. If B can't be 0 if we divide by 0, then it doesn't make any sense. There's no such thing as dividing by 0. Okay, well what does that correspond to? That's if b is equal to 0, then we get ax equals c, or x equals c over a. We only have one choice for x, and what we get is that if this is c over a right here, and what we got is a vertical line. So in that situation, we can't determine what y is because it's every value. Right? It's every y value on this whole line. It's perfectly vertical. Same thing happens if we have a horizontal line. We can't figure it out. But besides those very special cases, we can figure out what x is based on what y is, and what y is based on what x is. Right? The number of things that we have to figure out, the number of degrees of freedom. We were free to choose x as we wanted, but then y was determined. Y was fixed, and vice versa. If we picked y to be whatever we wanted, x was completely determined. What that means is we no longer have two dimensions that we're free in, right? We only have freedom in one dimension. And we pick which one it is. And so that's why what we end up with an equation like this is a one-dimensional object instead of something that would be two-dimensional, right? Once we pick one of the values in one of the dimensions, the other dimension is determined, and so we have a one-dimensional object. We lose a dimension by this equation. Okay. Stop for a second. Do you have any questions? Yes.
Sort of. I'm going to try not to compare this too much to what I know because people not in my field might not know the same things. But when you have a bunch of equations for this system and you pick one variable out of those, so, all right, when we have a circuit and we have 6 equations or 6 nodes, we need 5 equations and we pick one of those nodes as 0. So is that the same thing basically? Instead of doing it with 2 variables, we do it with 6 and pick one as.
Right, we had
Okay.
we had 2 variables here, and we had one less equation. We had 2 dimensions, one less equation, and then we made an arbitrary choice.
Okay.
For example, an extra equation that corresponds to saying x is equal to 0.
Okay.
Right? Yeah, same thing is going on.
I mean, I think we're covering that kind of stuff in this class.
Yeah.
I guess that's still linear, right?
Yes.
You're the doc.
Not yet.
So to speak.
Yeah.
Get it?
Metaphorically, but not literally. Yeah. So that's the direction that I'm going in, which is that. Well, let me just try to beat a dead horse for a second and go one dimension higher, which is the space that we live in. This wonderful world is 3D, at least locally, 3D real space. At least it looks like it, right? As far as we can tell. And so in this situation, or in that situation, we also have the concept of linear. Linear really just means degree 1. That's what we mean when we're talking about equations. If we say that they're linear, we mean that they have degree 1. All of the variables have the highest exponent 1. So in 3D, this was ax plus by plus cz equals d. And this is the equation for a plane. That's right. A plane, otherwise known as a 2D object. The 2D analogy of a line. It's a plane. It's one dimension lower, and it's flat, just like a line. Right? Just like a line is the flat thing in 2 dimensions. Right? It never changes its slope. We have the plane in 3D is the same sort of thing. It's flat. Okay. And this is linear. It's a linear equation. Degree 1. Okay.
So anything with any number of variables is still linear as long as the degree is 1.
Exactly.
Okay.
Yeah. So that's let's call this a definition. Okay. A linear equation. Can everybody see this, by the way? Is there anything in the... Okay, good. A linear equation is... I'll just write it like this. It's an equation of the form... Okay. I'm going to make just a very slight transition. In this case, we said the 3 variables were x, y, and z. We come up with an obvious problem here, which is that we've come to the end of the alphabet, right? And we only had 26 letters to start with anyway, so we're going to have to do something else. Instead of calling the variables x, y, and z, I'm going to call them x1, x2, x3, and so on. So I'm going to write an equation of this form. Also, I'm going to call the coefficients. What does the book call them? Should I use the same? Let's do our own. A1, x1, plus A2, x2, dot, dot, dot. That means you know what I'm getting at. AN, XN. I'm going to call it equal to C. This may not be the notation that the book uses exactly, but it's a simple translation, right? Maybe instead of A's, they use C's, and instead of C, they use a K or something like that. They're just letters. They represent an idea. Doesn't matter which letter we use. But this just allows us to have any number of variables. Okay. So a linear equation is an equation of this form, and I'm going to put a linear equation in variables. So we're talking about an equation with this number of variables. And that's it. That's the end of the definition. The only thing that makes this a linear equation is that all of these variables are degree 1. There's no x1 squared. There's no x1 squared. There's no x1, x2. Right? Variables are not multiplied by each other. Everything is degree 1. And that's what makes it a linear equation. So in a certain sense, this is simpler than the stuff that we talk about here and going forward towards calculus. It's simpler because we have the same kind of property we have here. If x and y are arbitrary, x and y are arbitrary real numbers, and I'm using this symbol. I'm going to go ahead and jump right into it using the mathematical notation. Is everybody familiar with this symbol? Okay. This means the set of real numbers. They're arbitrary. It's a little bit of an abusive notation. X and y are arbitrary real numbers, and z is determined, so long as c is not equal to 0. So this is very useful. It's a very useful way to deal with these things. Okay. So where does the complication come in if we're dealing with such simple objects? The complication comes in having a large number of variables. Oh, let's do an example. Where's the eraser? I get started talking about this stuff and I completely forget that I'm being recorded. I should probably try not to embarrass myself because it's going to be on the internet forever. James has been in my class before. He knows that's not going to last very long. I'm not going to be able to hold out. Okay, so let's start with an example. Okay, x plus y equals 1. In 2 and 3 dimensions, it's perfectly okay to use x, y, and z because we know we're not going to run out of letters. So we'll just stick with that just for the sake of feeling good about it. Okay, x plus y equals 1. And what's another one? 2x minus y equals 0. Okay, these are two different lines. And they're not these lines. This line and this line. They might be actually, I don't know. Okay, so everything that satisfies this equation, let's say, oh, this would be a negative slope, wouldn't it? Let's say it's this one. Okay, so this is line number 1. We'll call this line number 1. Ignore the fact that the lines aren't actually the right lines. Okay, and this line has a y-intercept of 0, so it's clearly not either of them either. So let's call this line number 2. Okay, so these are the two lines. And now what we've done when we draw a graph like this is we've represented all of the things, all of the pairs of two numbers that fit in this pattern, this fact, and this assertion. We should say this assertion. We're asserting that if we have two numbers, then 2 times the first one minus the second one is equal to 0. All the things that satisfy that give us some other line. So the things that satisfy both of them are this point right here. And we can think back to the old days whenever we had a very simple way of solving this system of equations, which was, in this case, somebody just yelled out at me. What should I do? What would you do?
Solve for x and one of them, and then plug it into the other.
That's a good strategy.
Do the minus thingy, but I always mess that up. So.
Yeah. Well,
You mean?
I go in the opposite direction usually. For this one, immediately I'm saying to myself I should add these two equations together because the y's will cancel out and I'll get 3x equals 1. And now I've got the value of x. So x is 1/3. Clearly this is 1/3 right here. It's going to be great if I get a negative number for y. Okay, so x is 1/3. I'm going to take that and plug it into one of the other equations, like this one. I get 1/3 plus y equals 1. And so y is equal to 2/3. And hey, it doesn't look so bad. 2/3. And that's it. We know that because these are straight lines, they don't cross anywhere else, right? The two lines are either parallel and they don't cross anywhere, or they are the same line and they cross everywhere. Every single point is the same. Or they're like this and they only cross at one point. So that's it. We're totally done. We have the solution. And so what we saw is that it takes two equations to pin down a solution, one specific answer, so long as those two equations are sufficiently nice. Right? Okay. Should we do one in 3D? Let's do it. What do you think? Another 2D one or in 3D?
3D.
3D, let's go for it. YOLO. Somebody told me yesterday that people aren't saying YOLO anymore. And I think that what we're saying is stay hydrated. That's like the new, we're going in the opposite direction. Or maybe it's, you only live once, you better stay hydrated. Okay, what was I doing? Let's come up with one. I'm going to do the first one, x plus y plus z equals 1. What will the second one be? Someone throw one out.
plus y